converted. But for the aerodynamics, it's not very easy. So now we have unsteady aerodynamics. This is the pure unsteadiness. Like you can see, that the non-circulatory part, we can just account for it straightforward way. We already did, right? So because why? Because it's an algebraic equation. So the lift, here it is. The lift and moment, non-circulatory, or the non-circulatory loads, this is an algebraic equation. Again, these guys at this time instant dictate that guy at the same time instant. There is no dynamics, so I can account for it very easily. But this is the problem. The circulatory one is the problem because it has dynamics. So let's see. We already did that. I'm just refreshing your memory. So if you remember, we have 5S, which is Wagner function, the step response, corresponding to the Dawson. Dawson is the frequency response. This was the step response. Again, there was no actually, unlike Dawson, there was no analytical expression for that. And if there is an analytical expression for that, there will be an infinite number of exponentials. So luckily, the Jones in 30s and 40s, they approximated the Wagner function as 1 minus a1 e to the negative b1s minus a2 e to the negative b2s, where they already determined the values. They are just constants, a1, b1, a2, b2. Okay? S is non-dimensional time, u t over b. So because we're doing dimensional analysis, I will make it dimension. So I will write the Wagner function as a function of dimensional time as it's the same thing, b1 prime times t, b2 prime times t, where the b prime is related to the b by u over b. Okay. So now I have this form. The output as a function of time, we already did that before. Take the Laplace transform to get 5p divided by the input, which is 1 over p. This is your transfer function in the Laplace domain. This was something like d of p equals 1 minus a1 minus a2 times p squared plus b1 prime, b2 prime, a1 b2, a2 b1. So you can see the b primes depend on the speed anyway. So the dynamics of your system depends on the speed. The dynamics means the dynamics dictate how fast and how slow your response. This depends on the speed. Jones approximated Wagner function with this equation, which is 2 exponentials, meaning we have 2 eigenvalues for the dynamics, 2 states at the end of the day. The transfer function will be second order. I'll complete it now. And actually, these are the locations of the poles. Jones gave the numbers for these. These were 0.3 and 0.0445, something like this. So 0.3, this is the location of the pole. This determines how fast you rise up, right? Because the settling time is 4 divided by this value, by the location of the pole. So now, because we went from non-dimensional to dimensional, the location of the new poles in the real time depend on the speed and the geometry. Okay? So these are fixed. This is the 0.3 and the 0.0445 by Jones, these numbers. But your actual ones depend on the speed. Anyway, it's just a side note. So if you're given the speed, I can compute the coefficients of this transfer function. So here we have b1 prime, b2 prime, divided by p squared, b1 prime plus b2 prime times p plus b1 prime, b2 prime. So from a transfer function point of view, this coefficient is n2, numerator 2, numerator 1, numerator 0, denominator 1, denominator 0. Okay, these are the coefficients of numerator and denominator. If I give you the speed u and the chord b, you can compute these coefficients. Okay? Any question about that? Any question? We already wrote this before. Maybe without the primes. But we already wrote this exactly before. And if you have a transfer function, you can write the corresponding state space model. So I can write down d by dt if it's a quadratic transfer function. This is x arrow 1, x arrow 2 is equal to some matrix times x arrow 1, x arrow 2 plus some matrix times the input. Okay? You can, from a transfer function, you can have infinite number of state space models. It depends on how you want to define your states. One particular way is called controllable canonical form, for example, which is on this form, 0, 1, 0, 1, and here is the negative of the denominator coefficient, so negative d0, negative d1. This is one particular form. It's not very unique in any sense, it's unique in control. So we'll stick to that and use it. So as you can see, this is the x's of the aerodynamics, A aerodynamics, X aerodynamics, so this is x dot, B aerodynamics times the input. Okay? So what is the input? What is the input? What is the input to Tidorson dynamics or Wagner? In here they are the same. What's the input? Do you have a suggested input? What?
Comes from a structure.
I'm sorry, I didn't
It comes from the structure.
That's great. That's great. Exactly. We want to do that. But in general, so this is a head point. But in general, if I want to complete this state space model, what input you should use here? You have a suggested thing. What is the input to Tidorson or Wagner dynamics? What's the input?
Motion.
The what?
The velocity.
The velocity at what point?
The half court.
No? 3/4, yeah. So this one, very legitimate. Actually, this is the most complete one in literature. Velocity, so some people use angle of attack, so you can write here alpha. Some people use alpha at the 3/4, this is a little bit better, right? Some people use the V at the 3/4 chord, this is even more better. We can see why later.
What about quasi-steady lift?
Very good. This is the most general one, which is the idea that I enforced in literature, the quasi-steady lift or quasi-steady circulation. These are all legitimate things, okay? But like Amir was saying is that, yes, I can use any of these now because it's small angle of attack approximation, they are all equivalent. Later on we will see the difference, 3 lectures from now. But I can use any of these, but taking into consideration that we're coupling 2 models. The output from the input to this guy should be the output from here, right? So I should use something that I can really get from here, okay? If they are all equivalent. If you are forced to something, that's okay, but if they are all equivalent, okay, let's use the most convenient one. Which one do you suggest to get it from here? We said angle of attack, alpha, only alpha. Well, alpha is very good because it's one of the states. Alpha 3/4, V 3/4, quasi-steady lift or circulation. Obviously, quasi-steady lift circulation cannot. Why? Because this is a structural model, cannot give you lift. Okay, so let's just rule out that. So you have V at the 3/4, alpha at the 3/4. The difference is just multiplying 1 by u, right? Multiplying alpha by u to get V. So we will use V at the 3/4, and we will use it positive downward. Okay. So do we have a place? Okay. Yes. This is your structure model. input is QC, output is V3/4. Why? Because luckily this guy can be the exact same input to the A arrow, which I can give you out of it the circulatory loads. And now we have our coupled system, right? So the output equation here in the structural model, the output equation should give me V3/4. Let's do that. Let's get the V3/4 here. This is easy. The V3/4 by definition was, if it's positive downward, this is something like H dot and U alpha dot and maybe plus alpha dot B half minus A. This was the V3/4 that we have been using. So this is already obviously written in terms of your states. So here it is H alpha, H dot and alpha dot, right? This is your V3/4. So 0 in H, the U in alpha, 1 in H dot, B half minus A in alpha dot. So we're done with this. This is the output of the structural equation. This is the matrix F structure. This is X structure. So we're done with the structural model completely. This is the output equation. This is the state equation. Yes?
Yeah. I saw the V equal for A, the input, not the output.
It's the output of structure, input to aerodynamics.
Oh.
So because the aerodynamics needs V3/4, we considered it to be the output here. So we constructed the output equation to make this guy the output. And we'll do the same here. If the structure needs the quasi-steady circulatory loads, so we'll make the output equation here to make the circulatory loads to be the output. We'll write it here right now, okay? So let's do that. So we have circulatory loads is what? It's just, yeah, we can write it. Just reminding you, what's the circulatory lift in terms of the 3/4 code, V3/4? Well, let's 2 by rho U B V3/4. If you write it like this is what lift you get. This is not the circulatory, this is what lift. Okay. What lift is that? Non-circulatory, no.
No, quasi-steady.
This is quasi-steady, right? Quasi-steady. Okay. So, actually I did not finish the... From this transfer function, you can create a state space model, use MATLAB or any standard method. This is one of the standard methods. It gives you the A, B, and the other two matrices. It has to give you. So actually the coefficient of the denominator gives you the A matrix, and the coefficient of the numerator, they fill the output equation, okay? So, they fill the output equation. So here is, let's fill the output equation together. If you read in the any control book, textbook, this, here comes the coefficients, N0 and N1, but we have this term N2, we have to subtract negative N2 G0, negative N2 G1. This is multiplied by x arrow 1, x arrow 2, plus here is the N2 term times the N. If I use the V3/4 here, what will I get here as an output? So if I write equals, what will I get? Can you think a little bit? Can you tell me? if you use the V3 quarter, what you will get here. This state space model, just reminding you, this state space model is exactly corresponding to this transfer function, which is exactly corresponding to Wagner function only. Wagner function, it reaches unity in infinite time, right? Wagner functions reach unity. So this means that steady state wise of it, if you apply any something time variation here, but steady state wise, you will get what? You will get the same thing, right? So this is actually the unsteady version. Because this system has a unity DC gain, whatever you put here, you get it there, but you get the unsteady version of it. Okay? So this is the quasi-steady. Here is the unsteady version of it, which means if you apply a step input here, this system will give you the transient response of this guy, which will reach unity to reach the exact same value infinite in time. Do you get this thing? What I'm trying to say is that this function, this transfer function has a unity DC gain. What do you mean by unity DC gain? If you apply state input 1, you get 1 far out in time. Okay? So if this is V3 quarter, you will get the same amount of V3 quarter far out in time for applying step input. So this will be the V3 quarter. If you want to call it effective, call it effective. If you want to call it unsteady, call it unsteady. This is the unsteady version of the V3 quarter. Okay, and what to do with it? Well, just multiply. If this is your equation for quasi-steady, if I used here the unsteady version of it, this will be the circulatory. That's it. So this is the circulatory, and this is the effective or unsteady. That's it. Okay. I'm just stressing this because it's a really subtle point. Maybe it doesn't worth all this time, but just to give it to you in a rigorous way. For example, if I put here alpha 3/4, I will get the alpha 3/4 unsteady, and I will use this exact same relation, so I'll have u squared here. If I use gamma quasi-steady, which this is what I did before, gamma quasi-steady, you will get the gamma unsteady or gamma effective. Let's say gamma effective, and here it will be rho u times gamma effective. Okay, so this thing is just a constant multiple of the unsteady thing. Okay, so knowing that, we can write